For a sequential processor with a slow and a fast memory, recall the basic concept of the balance point of the machine. In terms of our cartoon, it's R, the peak rate of processing, divided by peak memory bandwidth. Let's also recall the historical growth trends of R and beta. The rate of improvement in computation far outstrips the rate of improvement in communication. This gap doubles about once every 5.5 years. So for your algorithms, what does this mean? It suggests that it might be beneficial to trade off more computation for less communication. Let's be a little bit more analytical about this claim. Start with the DAG model of computation. In it, you characterize a computation by two components. The first is the work, or the total number of operations, which I'll denote by W, or W of n. The second is the span, or critical path length. We call that D of n, or D for short. Let's augment this representation to reason about slow-fast memory communication. In particular, remember that you can, at least in principle, count the number of slow-fast memory transfers. I'll denote these transfers by Q. Q will in general be a function of the problem size, the size of fast memory, and the transaction size. I'll also assume by convention that W includes the count of Q. So for example, if Q is 3 and W is 10, then that means there are 10 minus 3 or 7 operations that are non-memory transactions. Let's also modify our machine cartoon a little bit as well. As before, there will be a large slow memory as well as a small finite capacity fast memory of size Z words. When data moves between slow and fast memory, it does so in transactions of size L consecutive words. In addition, let's let the processor have P processing cores. Let's assume each core can execute some number of operations per unit time. We'll call that rate R0. Let's model the operation of memory by analogy to the way the cores work. Each transaction initiates a data transfer across these L wires in parallel. The time it takes for a word to go across a wire is beta 0. In other words, beta 0 is the analog of R0 in this cost model. And remember, W, D, and Q count the number of operations, ignoring these costs. Put differently, we usually compute W, D, and Q assuming unit cost operations. But in a high-performance setting, let's try translating unit costs into real costs to see what they imply about the overall system. Conceptually, you can account for non-unit costs by transforming a unit cost DAG. For example, consider some node in the unit cost DAG. Suppose this node is one of the compute operations. Then executing it costs 1 over R0 time units. So we could replace this single unit cost vertex with a sequence of 1 over R0 unit cost vertices. Now, what if a node in the DAG instead represents a memory transaction? Let me suggest that we model transactions in the following way. First, there's a latency cost which is the same as the latency cost for the compute operations. In other words, the memory transaction became 1 over R0 unit cost nodes. After all, a memory transaction is just another instruction, so it should roughly share the same instruction processing costs as any other instruction. Next, let's also say that the words of the memory transaction can be in flight concurrently with compute operations. In terms of the DAG, that's an additional set of L over beta 0 fully concurrent nodes. Inserting them as concurrent nodes mean they shouldn't increase the critical path length. However, by putting them in as explicit nodes, we'll have to pay for their cost. Most real memory systems behave something like this. That is, there's usually a separate memory controller or network processor onto which you can offload communication. So, what's the best case execution time for this DAG? To start, the usual work and span laws apply, just scaled by the processor speed. There's just one extra cost due to communication. That is, for each transaction, we have to pay for the cost of these nodes. Now, if you've done a good job designing the algorithm, the critical path is short. In this case, when is this right-hand side minimized? That's right, it's basically when these two arguments are equal. Now, remember the historical growth rate trends? Of course you do, because what better way to beat insomnia than to always be dreaming of exponential scaling trends? From the trends, if you want to benefit from transistor scaling, then you need the compute time to dominate the communication time. I like to call this idea of making compute time dominate communication time the principle of balance. That is, our collective goal, whether we design algorithms or we design systems, is to make it as easy as possible to achieve balance. That's what gives us our best shot at scaling into the distant future. Now, let's start with this relation and massage it a little bit more. On the algorithm side, your goal is to make the left-hand side as large as possible, knowing that the right-hand side is subject to inevitable scaling trends that cause it to grow over time. What about the system side? On the system side, your goal is to try to keep this small to help the algorithm people out. Now would be a great time for some quick exercises to see what this balance principle, derived from the modified DAG model, implies.